Today we start a new chapter. It's on reflection and transmission, and we'll have, just one lecture on this. That will be enough for us to be able to do some problems tomorrow. So tomorrow is problems, and then we'll continue with this chapter next week, right? And remember, tomorrow is the lecture's at 3 p.m. in here, 3 p.m. Pacific in here. Okay, well, the basic idea here is this. When you have a medium, and by medium here I mean something, a substance, in our case, usually a fluid, which supports waves, where you can get wave propagation, sound in our case. When you have two mediums, when you have an abrupt discontinuity in a medium, so basically you're going from one medium to another medium, then in general, what you're going to have is, and a wave comes along there, in general, part of the energy will be transmitted and part will be reflected, okay? In unusual cases, which are important, you can get perfect transmission. We will certainly talk about that, okay? So here's an example. This is not acoustics, but it's a nice educational system invented during the Cold War when a lot of money was dumped into education. I've got two of them here. This is a torsional wave apparatus. So the idea is this. There's a thin metal rod, steel rod, running through here. I think you can see. And then there are these, so in a rod like that, you can have torsional waves. I don't know if you guys got to those in 3119. I never get to it. Did you guys? Yes, you got to them? Okay. If you have a rod like this and you momentarily twist the end like this, you'll generate a torsional wave or property line. And they're simple waves. They obey the wave equation, as I guess you know. Okay. So typically torsional waves travel very fast. So that's why these cross arms are here. This supplies inertia that slows the wave way down. And let me demonstrate it here. I've connected these two dissimilar mediums, right? You can see there's a difference here. These cross arms here are twice the length of this. But just to show the basic idea here, I've fixed the interface right here. So we're just going to get a reflection. So if I send a pulse down here, you can see the pulse is reflected at the end and it comes back. You'll note that it happens to be inverted. We'll talk about that later. But if I send out an upright pulse, see it comes back, it's inverted, right? It's very difficult to do continuous waves here because you're going to get a standing wave when you have this reflection. So it's good to demonstrate standing waves, but not traveling waves. So the idea here is this. These are now, we're going to send a wave here, a pulse, down here in this medium, right here. And when it hits here, this is a different medium now. So in general, there's going to be reflection and transmission. Let me demonstrate that. Let me steady these things. Okay, so I'm going to put a pulse in here. So you can see there was a reflected pulse and there's a transmitted pulse that came and bounced off the end and came back there. And it doesn't matter, of course, which way you're going. This is reciprocal. If I do it from here, see the same thing happens? You notice these waves travel quite fast. Why is the wave speed greater here? Well, remember the wave speed in general goes as the square root of a stiffness divided by an inertia, right? So the stiffness here is the torsional stiffness of this rod. It's the same type of rod here that's twisting as here. So the stiffness is the same, but what about the inertia? Yeah, this clearly has greater inertia. Now quantitatively, what should be important here is the moment of inertia. That's what is going to slow down a wave. It's the moment of inertia. And you may remember from mechanics that the moment of inertia is proportional to the square of the length here of these rods. So we've doubled the length of the rods. The wave coming here sees a doubling of the length of the rods. So the moment of inertia has gone up by a factor of 4. So the speed, oh, it's gone down. I'm sorry. If we go this way, if we go this way, the inertia has gone down by a factor of 4, right? Sorry, I'm getting confused. The inertia has gone up by a factor of 4. So we expect the speed to go up by how much? Twice, because it's the square root. The speed, wave speed is the square root of the stiffness. Yeah, I'm sorry. Maybe I should start writing this on the board. Okay, so the inertia goes up by a factor of 4. We'd expect, because the speed of waves is inversely proportional to the square of that, we expect the speed to go down by a factor of 2. Here. You can see it's definitely faster. I've done this demonstration for years, maybe 10 years or something like that. And I never looked at it quantitatively. So several days ago, I just checked. I disconnected them and checked the speed. This speed is much greater. It's like 50% or more greater. So what's going on there is there could be something wrong with the theory. But my suspicion is this apparatus has gotten much more use than this one. You notice how it's missing rods here and they're all kind of twisted, and it could be that the stiffness has, over the years, many years, the stiffness in this rod has gone down. The elastic limit has been exceeded, and it may be that the stiffness, that's my guess, but I'm not sure. I need to check the theory to make sure it's right, but the theory is so simple here. The speed should really be cut in half here. But, or when you come in this way, the speed should double. But it like I say, it's substantially more than that. But I'm not sure why. Okay, so the way you learn this stuff is you dive into specific examples of a wave encountering a discontinuity in the medium. Okay? But before we do that, we need to set some sort of general definitions and discuss the general problem. So we're mainly going to be concerned in this chapter with sound going from one uniform medium to another uniform medium. This is an example of that. This is a uniform medium here. Another uniform medium there. So by uniform, we specifically mean constant density, constant speed of sound. And we'll look at a planar interface between the two mediums. Okay. Now, in general, it can be more complicated than that, right? But that problem gets difficult to solve, except in a few cases, which we'll discuss at the end of the chapter. Now, here's something that's interesting. We're, of course, considering fluids in this course, right? However, when you have sound, here's sort of the general problem. Here's one uniform medium. Here's another uniform medium. We have a planar interface here. When you have normal incidence, and by that we mean the wave is coming in here perpendicular to the interface here. If this is a solid, let's say here, our theory will still apply. And this can be a solid too. The reason is the difference between solids and fluids is that a solid can support shear waves. A fluid can't. But in the normal case here, if we excite a transverse wave here, if we excite a compressional or longitudinal wave in a solid here, and part of the energy is reflected, part is transmitted, by symmetry, we're not going to excite any shear waves. So as long as we don't excite any shear waves like this, go like this in a solid, our theory will apply. So we will be able, and we're going to do problems, quantitative problems, where one or both of these could be solids for the normal incident case. For the oblique case, I think you can probably see here that what's going on at the boundary is much more complicated. And if we come in with a longitudinal wave here, let's say this is a fluid and this is a solid. We come in with a sound wave here. Because of the angle here, it will excite both shear waves and compressional or longitudinal waves. And that's beyond our theory, right? So we can't apply it there. We're going to take the waves to be traveling plane waves, except at the end of the chapter where we'll do this really interesting method called method of images. Some of you may know it from electrostatics. amazing. You can very easily get answers to problems that look quite complicated. Something else I was going to say. What is it? I can't remember. Oh, yeah. Now, I should point out here, we pointed this out before, but it's worth saying it again here. We're going to consider nice monofrequency waves, right? In a more practical case, perhaps, you have some wave packet here, or a pulse, or it could be a pulse like you just saw there. We can always, with Fourier analysis, we can always superpose. This is all linear here. Our theories are all linear here. So we can create one of these types of waves from as a superposition of monofrequency waves, right? Okay. So this medium has a wave impedance, or specific acoustic impedance. It's just the density times the speed of sound. And similarly, this wave has it, and this is going to be different here. These, we're going to find that it's very convenient to deal with impedances here for several reasons, and you'll see why. But I just want to remind you we have impedances here. One of the reasons it's important, just looking ahead here, is that in some cases, what's going on here, and by that I mean the amount of energy reflected compared to the amount of energy transmitted, only depends upon the specific acoustic impedances. It doesn't depend on the separately on the density and speed of sound, only on their product. That's a really nice simplification. Now, it doesn't happen all the time, as you'll see, but sometimes it happens. So moving along with the general problem here, we have a wave coming in at some angle. The angle of incidence is the angle from the normal here, so it's this angle right here. That's the angle of incidence. This is I can't reach there. This is the angle of reflection, the angle from here to here. And in general, the angle of transmitted wave is different, as we will see. So for plane traveling waves, here's what we have. This is a plane traveling wave. This is the incident wave. That's what the I stands for. This is our usual wave propagation, phase factor in 3 dimensions that we discussed in the last chapter. There's a reflected wave. So the pressure, these are pressures. Some pressure amplitude at the origin. This is the pressure amplitude at the origin here, these capital P's. And there's an R here for reflected, and then finally transmitted. Now, we're dealing with complex instantaneous pressures here. These amplitudes are in general complex. That's why they are emboldened. And sometimes they're real, but I'll tell you right now, once we get away from the simplest problem, which we'll get into today, you have to deal with complex amplitudes here. And what that means is there's amplitude and phase here. There's amplitude and phase information in this, and we're going to need that. And the reason we're going to need it is, before we get into that. So, on a computer, it's easy to embolden these. And we're sort of following what KFCS do with complex quantities, as I mentioned previously. When you write this stuff, it turns out you can get away with not writing, when you handwrite something, you write a pressure. When we write this, write something like this, it's almost always clear and understood that these are complex quantities. And in the end, if you need to, you're going to take the real part, right? But if only occasionally is there a problem where you need to distinguish, make sure you know that these are complex. When you do that, when you hit that, you can just put an underline. You can put an underline there. How did Professor Scandrett handle this last quarter when he was handwriting? Like in my problem set solutions, for example, those are all handwritten at this point, right? How did he handle complex quantities? Or maybe you guys didn't hit it that much.
Professor Baker did the tilde.
Oh, that's right. You guys had Professor Baker. The distance learning students had okay. Oh, yeah. Okay, I know Baker. Okay. I was curious about Scandrett. So anyway, maybe I'll learn. You don't have to, the distance learning students, I was just curious. You don't need to phone it in. That's okay, unless you want to. Okay, so this is a little bit of a warning. You'll see, I think, in the problem sets, occasionally I may underline it when it's very critical, but otherwise it's just going to be sort of understood, okay? And incidentally, before I typed these lecture notes were typed only, I think I might have told you this, is roughly 4 years ago. And I've taught the course, twice as many times as that, going back, probably 8, maybe probably 10 years, roughly. I just wrote it. I just said, well, it's understood, and the students seem to get away with it. So, okay. Now you'll notice something. We've already done something here. I sneaked it in on you. Look at this. I've got this K sub I, K sub R, K sub T here. But what about the omega? I don't have an omega I, omega R, omega T. Well, it's physically reasonable. If you're hitting a boundary, you've got a wave coming here at some frequency. The frequency of the reflected wave has to be the same as the frequency that's coming in. And the frequency has to be the same there. Because otherwise, one easy way of saying this is, if those frequencies, let's say the frequency coming in was greater than the frequency of the transmitted wave, then you're going to have wave crests building up at the interface. If you've got, the rate of crests coming in is greater than the rate that's going out, they're going to be building up there. That can't be. This is we're looking at steady state situation here. Nothing's changing at time except the usual oscillations here. There's nothing else changing in time. We will explicitly show this later. Okay, actually it won't be today, but on probably Monday. We'll explicitly show that when you impose boundary conditions, all these frequencies have to be the same. But I think it's very reasonable, and it's much simpler just to assume it right now. Okay, so we need some quantities here. What's important? Well, it's not going to surprise you. We have what's called the reflection coefficient. This is a general idea, not just in acoustics, but electromagnetic waves and other kinds of waves. It's defined to be the reflected at the interface, at the origin, the complex pressure amplitude at the of the reflected wave divided by the complex pressure amplitude of the incident wave. And all that's important here is the ratio. If we double the amplitude of the incoming wave, we're just going to double the amplitudes of the reflected and the transmitted wave. This is all linear. So things scale. So it's natural to define this ratio here. Also, similarly, we have the transmission coefficient. So it's similarly defined. These are what we're after. Okay, those are the critical quantities here. From these quantities, we can get, and the parameters of the medium, we can get other important quantities. And before I go into that, let's see here. And so note that these are in general complex. That's why they're emboldened. So the reflection coefficient, if you've got a reflection coefficient of 1/2, the amplitude of the wave being reflected is down by a factor of 2. Okay, but there's another issue there, and that's the phase of that wave relative to at the interface here. The phase of that wave. And this can be important, as you'll see. So we've got both of those pieces of information in here because it's complex. So one of the key things we want to deal with here is energy. We have to connect this with energy. All right, and here's where it gets a little messy. Okay, but you'll get used to it. This doesn't look too bad at first, but we're not done with this introduction here. So following KFCS, we define the intensity reflection coefficient. R sub cap, that's a capital I, that's an aerial I. Doesn't have the whatever those things are called on there. That's an I, like this I. So it is the fraction of the reflected intensity. We have an incident intensity. Some fraction of that is going to be reflected. That's the intensity reflection coefficient. Similarly, we have the intensity transmission coefficient. Now, we know for a plane traveling wave, we have a formula for this. Remember, it's just the peak pressure squared divided by 2 times the impedance. Remember that? So we can go ahead and write those down here. And now, because the reflected wave is in the same medium as the incident wave, these denominators here cancel, and we end up with this really nice, simple result. The fraction of the intensity that's reflected, which we call the intensity reflection coefficient, is just the square modulus of the reflection coefficient. What about the transmission? Well, we have the same idea here. This is the fraction of the intensity that is transmitted. We use our formula. And now, because the mediums are in general dissimilar, because they have usually they're going to have different acoustic impedances, that survives. So it's getting a little bit more complicated here. So the fraction of the intensity that's transmitted is not simply the square modulus of the transmission coefficient. You've got this factor in front of it, the ratio of the wave impedances. So it's starting to get complicated, right? And we're not done, because you might hear, I'll explain this. You might think here that the fraction of intensity that, you got a fraction of the intensity that's reflected, a fraction that's transmitted. If you add those two, you should get 100%, right? Whatever fraction of the energy is reflected, the fraction that's transmitted has to be 100% minus that, because we have to conserve energy. That's true for normal incidence. In normal incidence, it's clearly true. There's no question about it. The intensity coming in here, part of it goes this way, part of it goes that way. The sum of this intensity plus that intensity has to be the incoming intensity. That's energy conservation. However, it's not true for oblique incidence. This is where it gets a little complicated, okay? So let me explain this to you. It's worth explaining this right now. So we do have this formula for normal incidence. The sum of those two has to be 1 or 100%. So let's see what happens at oblique incidence here. What you have to do in this case is to be careful about energy conservation. You have to consider some cross-sectional area of the incident wave. So I have this sound wave coming in here, okay? I focus my attention on some cross-sectional area here, perpendicular to it. So what I know is true is that the power, the energy per unit time, coming in here, has to be the power here plus the power there, right? That's energy conservation. Now, we will show later on, and it's not going to surprise any of you, I don't think, that the angle of incidence here, which I said earlier is this angle, compared to the angle of reflection, which is that angle, is that they're equal. The angle of incidence equals the angle of reflection. That's generally true, and you've probably seen this before. However, the angle of this angle can be different here. So this area will equal this area. AR will equal AI. But AT can be, in general, will be different. And in fact, in this particular case, you can see AT is bigger than AI, right? So that has a consequence here. Let me show you what it is. To get at it, we define yet some other, so this is why it's getting a little confusing, okay? We have another set of coefficients here. These are called the power reflection coefficients. So I focus my attention on an area here. The power is going to be the intensity times the area. So the power reflection coefficient is the power coming in divided by the power reflected. And because AR equals AI in this case, here, because the angle of incidence equals angle of reflection, it's very simple. Okay? This power reflection coefficient is identical to the intensity reflection coefficient. However, in the transmission case, the power transmission coefficient, same idea here. But now, because these two areas are different, this ratio is not going to be 1. All right? And you remember, the intensity transmission coefficient is not equal to t squared. You've got the ratio of the wave impedances. So that complicates it a little more. Now, the whole point that we want to make right now is, besides defining these things, quantities that we'll deal with later, is that energy conservation tells me that this plus this has to be 1 or 100%. It doesn't tell me that, that Ri, it doesn't tell me this only equals 1 for the normal case, okay? So you just want to be careful, and we'll point this out when we hit it, that it's tempting to think that energy conservation tells you this is true, but because of this area problem here, this is not true. And in fact, I think this will come up in a problem. In fact, okay, so because of this, these are positive definite, they're non-negative, right? So assuming you have some reflection here, this is going to have to be less than 1. I think we're going to encounter a homework problem where this is actually greater than 1. Okay, so that's a dramatic case of this, the fact that this is not true. So I'm pretty sure that's the case. We'll see. Okay, so is that it? Yeah, finally, we've sort of laid the groundwork here. Looking at the general problem. And you're not expected to grasp all this immediately. Okay, you only get it by working with it. And what do I mean by working with it? Well, we solve problems. And the simplest, and like physicists always do this, we start with the simplest possible non-trivial problem here. And that problem is a single interface, planar interface, with a plane wave coming in normally or perpendicular. We're going to have a transmitted wave and a reflected wave. We want to find the reflection and transmission coefficients. And we want to verify energy, we'll check energy conservation. Okay, so here's the problem. Well, I didn't have to go back there, I guess. So here it is. We've got an incident wave in medium 1. We'll naturally call the interface, we'll call that x equals 0. Everything is only a function of x. Nothing's a function of y and z here. Okay, so our acoustic pressures are, now we're going to make a slight change of notation here. The incident pressure has some, complex, the instantaneous incident complex pressure has some, in general, some complex amplitude at x equals 0. Here's the wave factor. And now this is not an I anymore, it's a 1. Because this is in medium 1, it's natural to call this K1. Now before, in general, we called this Ki coming in here and Kr going there. And the magnitudes of those Ks have to be the same because the wave is in the same medium, right? But the directions are different. So we'll handle the oblique case later. But for right now, let's make the notation as simple and as natural as possible. We're going to call this K1. And our dispersion relationship is omega over c. The same omega has to be, as we explained, has to be everywhere. And the c will be C1. For the reflected wave, what do I do? Well, all I change here, in addition to these subscripts here, the r's, I keep the frequency the same. The magnitude of the wave vector will be the same. Only the sign changes here, because it's now a left traveling wave. Okay, and the transmitted wave will be traveling to the right, so we have a minus sign similarly as the incident wave. But we have a different magnitude of K2. It's given by omega over C2. Okay, so this is pretty simple, right? Now we can't do anything. We can't make any more progress. We've just really scratched the surface here. To make any kind of connection here, in order to find the reflection and transmission coefficients, we have to impose boundary conditions. Right now they're not in the math. So what are the boundary conditions? Well, the pressure has to be continuous across the boundary. So I've got a boundary here. And at any instant of time, I look at the pressure just on this side of the boundary and compare it to the pressure on this side. If those two pressures aren't the same at every instant of time, there's going to be a net force, right? Pressure times the area, there's going to be a force. And how much mass do I have right at the interface there? 0. There's no mass there, right? There's mass. If I take a slab, there's mass of the fluid. And there'll be some of it, different density will contribute here, but contribute there. But that's not important because when I shrink this down, what happens to the mass? It goes to 0. So you can't have a finite force on an infinitesimal mass. You would have infinite acceleration. So a physical way of saying that is if you could somehow arrange to have a discontinuity in pressure, it will instantly go away because there'll be essentially infinite acceleration to keep that pressure the same on either side. So we have to have continuity of pressure. We also have to have continuity of particle velocity. So if you look at the interface, let's say that you have this particle velocity here, right in our sound line, a particle velocity here. If the particle velocity here at this point were less than the particle velocity here, what would be happening at the interface? there would be separation. Okay? Right, and I guess there's a name for that. All Navy people know it, although not in this context. What? Cavitation. That would be cavitation. Highly nonlinear, we're not doing that. Okay? So it's probably possible, I've never seen anything on this, but it's probably possible to have actually a separation of a fluid here between two different media. That would be cavitation. But for linear acoustics, we've got to have continuity of particle velocity. Oh, and the other possibility is that the particle velocity here is greater than the particle velocity. Now, this fluid would be penetrating the other fluid. That would be weird. That may be possible, I don't know, but it's a highly nonlinear situation. So we've got to have continuity. We have to have these two boundary conditions. So at x equals 0, that's where the boundary is, the interface. So at every instant of time, at the boundary, at x equals 0, we have to have the instantaneous pressure on the left side equal to the instantaneous pressure on the outside, and we have to have the particle velocities being the same. Now it's tempting at this point to substitute our expressions. We have expressions here for the pressure, for these pressures. We can get the expressions for the velocities through the impedance, but it turns out it's better here. This problem can be done in a much simpler way if we take the ratio of these two. So I take this divided by that must equal this divided by that. So I get this equation. Now the reason we're taking the ratio is we're headed towards the use of the impedance. It's the simplest way to utilize the impedance. For example, we know what this has to be. If you think of just the second medium there, the transmitted medium, we have a plane wave traveling in the positive direction. What is this? It's going to be rho c for that, rho 2 c2, right? So we've gotten rid of that in terms of the parameters of the medium. So that's really nice. We could do a similar thing here. We have to go through a little bit more work. And you can do this actually in your head. Here's one way to do it. This ui here, the incident particle velocity, will be the instantaneous incident pressure divided by R1, right? So I can solve this for U1, plug it in here. I can solve here for the reflected wave. We have a similar relationship, except now there's a minus sign, remember, because it's traveling to the left, not to the right. This is maybe the only reason why we carried along those plus or minus signs in the last chapter. I don't know if it's worth it, but I think that may be the only time we're going to use it, but I'm not sure. Okay, so that's very important. You have to recognize here because this is left traveling. We have to have a minus sign, as we saw in the last chapter. So you just substitute, and like I said, you can do this in your head. Substitute, get rid of the u's here, put it into here, and here's what you get. I've switched the order. I've moved this over here. This is just R2. And here we get this. Remember, this is all at the interface, so we need to denote that here. And now I can divide numerator and denominator by pressure. And so it's physically, we know this physically, all that's important is the ratio of the pressures, because this is all linear. And we see it here. And what is this ratio? Well, that's what we call the reflection coefficient. So we get this, and now we invert. This expression has to equal this. We invert, and we solve for the reflection coefficient. And we get this. And I'm trying to remind you here, when you look back on the notes, if you do, this is only, we're doing normal incidence here, okay? So I put a box around this. It's an important equation. We're part way. In some sense, we're halfway through with solving what's going on here. Although there's a lot of interpretation that we're going to be doing, okay? But from a mathematical point of view, once we find the reflection and transmission coefficients, mathematically, we know everything we need to know. We can compute then. Then it becomes just an computational thing. Now, I've done something here. This is complex in general, right? Why didn't I embolden that? Anybody see why? In this case, it's always real. So now it can be positive or negative, right? Depending upon the relative, the relative values of R1 and R2, but it's always real. So the reflected sound wave is either perfectly in phase or perfectly out, perfectly in phase or 180 degrees out of phase. And it can be both. It depends upon this. So we can handle that with just a sign, plus or minus. So there's no need to consider this to be complex anymore. So that's why I didn't embolden it there. Now, I wonder, this came pretty easily, didn't it? And did we use this? No, we didn't use it. We only used what the impedance for a plane traveling wave is. And you remember, it was a homework problem. The impedance here, even though we derived it in lecture for a monofrequency wave, it's true in general. Remember, we did that problem. So it took me a few years to appreciate all this, incidentally. Okay. This doesn't happen overnight. You have to teach a course a number of times. So anyway, our result is, the only thing we've assumed in our result is normal incidence. It works, it'll work for this. It'll work for this, right? Doesn't have to be a monofrequency wave. So that's nice. It's more general. All right. Let's see if I'm... Right. Okay, that's what I just said is right there. All right. So, like I said, in some sense, we're halfway done. Clyde would say we were half. Oh, you guys don't know him. Anybody have him in a? Oh, he may be our next dean. Nobody knows. It's neck and neck. And you think, Washington politics is bad. You have no idea. It's really nasty in academia, including NPS. It's unbelievable. Okay, what about the transmission coefficient? Well, we could go through everything we did before, and I guess, but there's no need. Usually when you're solving simultaneously for quantities and you have some mathematical structure, once you've found one unknown, the other ones always kind of fall in place. Remember that when you do like linear algebra? This is linear here. So the easiest way to get at it is look at our pressure boundary condition here. We know that the pressure has to be continuous at the interface. That's what this says. If I divide by the incident pressure, okay, and evaluate it at x equals 0, I get this relationship. Oh. If I divide by the incident pressure, I get this relationship. And then if I evaluate it at x is equal to 0, okay, that's just going to be our ratio of the capital P's. This is going to be the reflection coefficient. And this is going to be the transmission coefficient. So we have to have this relationship in the normal case for reflection and transmission coefficients. And this is not energy. Some students think this, look at this, and even I've done this. You look at this and you say, oh, it's energy conservation. No, this is not energy conservation. We're dealing with amplitudes here. This is not directly related to energy conservation. And anyway, it's not right anyway, because energy conservation, if you wanted to think in terms of energy incorrectly, in terms of energy conservation, you would have this on the other side with a plus sign. You would say R plus T has to equal 1, which is not true, because energy is proportional to the square. So what this is continuity of pressure. That's what it is. Even though if you're not careful, it looks like it could be energy conservation. It's definitely not. So that allows us to determine the reflection coefficient, the transmission coefficient from the reflection coefficient. So it's a little bit of algebra. You form this sum, and it simplifies, and you end up with this relationship right here. And again, this is for normal incidence. So mathematically now the problem is solved. But like I said, we've got some work to do here. We want to look at the consequences and physically interpret some of the results here. Now, one of the things you want to note here is all that's important. Again, once we know R and T, we essentially know everything. To define R and T, all that's important is the ratio of the wave impedances. That's all that's important. So you can go in there and change the medium. You can change these mediums. If you keep the ratio R2 over R1 the same, you're not going to change R and T. The system is mathematically identical. So it can look very different. You can have different fluids in there. But if the ratio of R2 to R1 is the same, it's, the waves are going to, they don't care. The waves are going to behave the same, even though they look like they could be different because you have these different fluids, or solids in this case. So that's a nice simplification. We'll find that it doesn't hold for the oblique incidence. Oblique incidence gets more complicated. So let's go along here. This is one of the ways you learn that stuff that I did in the introduction there that looks complicated. It starts off real simple, and then we started talking about intensity and transmission coefficients, and you feel a little uneasy. And then when you get to the power, you're lost, right? So one of the ways of appreciating that is let's find out what they are here. So remember, and you may need to look back, the intensity reflection coefficient is simply the square modulus of the reflection coefficient. And we can unbold initially. We don't have to worry about the modulus here because this is real. So it's just going to be r squared, so it'll be this, all right? And the intensity transmission coefficient, you remember, that's not going to be that. It involves the ratio here because the medium has changed, as we discussed. But you just calculate this, and you get this. Okay? Now, in this case, for normal incidence, the sum of these two has to be 1. Because when the wave's coming in normally, the fraction of the energy that is reflected plus the fraction that's transmitted has to be 1, has to be 100% by energy conservation. Because we don't have that area problem. All the areas are the same. When you look at the area, the transmitted area is the same because it's all normal. So is it obvious to you that the sum of this it's not obvious at all. So let's confirm it. And again, this is what researchers do all the time, either analytically or there are experimental analogs to this too. This is called a check. And in fact, I don't know if in these notes, I thought I did it, but maybe I didn't. We're going to put jumping to the end here. We're going to put a check mark here. This is if this does not equal 1, we would have made a mistake. We'd have to go back. It's got to equal 1. And if it doesn't, we got to go back and find the mistake. So let's go through this. Here's the intensity reflection coefficient, intensity transmission coefficient. They both have the same denominator. That's nice. Bring them underneath here. And you can see that we have a simplification here. This is going to be plus 2r. And this is a perfect square. So sure enough, we end up with 1. So I'm going to add a bold check mark here. That doesn't mean that it's complex. It's just for emphasis. Okay? That was sort of a joke, and nobody laughed. But I'm not surprised. Okay. All right. So. Now, let's begin. What time is it? Okay. Let's start to interpret, look at the consequences here. You'll notice, as we said, the reflection coefficient here, it's on the previous page, is always real. Or maybe, yeah. It can be positive or negative, or 0. So, as an example, suppose we have air on the left, the incident medium is air, and the transmitted medium is water. Okay? If you go back and look at the formula, you'll see that the reflection coefficient is positive. What that means is at the interface, I've got a wave coming in. The pressure wave coming out has less amplitude. Okay? That's pretty obvious, right? It turns out it's not less by a lot, but it is, in general, it's going to be less. But they are in phase because this is positive. So they're in phase. If we did this, if we switched it, if we had water to air, now if you go back, you'll see that it'll be negative. So now the reflected pressure is 180 degrees out of phase from the incident pressure. Now you might say, well, okay, why am I saying this? Well, you just have to wait down the road. Phase plays a big role in all waves, and especially acoustics waves. So it's just good to check this out. Finally, the interesting thing here, and it's very natural. I don't know if it's a rigorous argument, but we can see from the, without looking at the expression, but you can look at the expression here. When the two impedances are the same, what happens? When the two impedances are the same, all the energy goes through. And that's important, right? It's obviously important for the military, because somebody could be, you could be hit with a sound wave because somebody wants to detect you, right? Especially underwater, an underwater situation. If you can absorb all that, not get any reflection back, if you can cloak yourself in that way, that would be obviously highly advantageous. So we'll talk a lot more about that in this class. But we're seeing, I just want to point out the obvious importance of this. Okay. So, all that's required is that the specific acoustic impedances are the same. You can have a different density on the other side, right? You can have twice the density on the other side. If the speed of sound is 1/2, then what's going to happen? Right, we have the same. So here's 1 and 2. And you remember, R is, we'll just call it rho C. So if I've doubled the density here, but I've halved the speed of sound, the wave impedance is the same. We have no reflection. So that's a remarkable fact. And we're going to talk a little bit more about this Monday, okay? But what I want to show you right now is an interesting demonstration. And I actually remember this from high school. And that was a long time ago, okay? So what I'm going to do here is uncouple these, get this one out of the way. And now we're going to put here, this is called a dash pot. And there's a fluid in here, water, and then there's this, I had to tape it because it's broken. There's a metal disc here going through the fluid, so the water. So it looks like this, okay? So this is, there's not much distance clearance there, and there's a fluid in here, in this case water. People do this with gas too. This is really, it strongly dampens. If you can feel this, it really strongly dampens. And it's called a dash pot. The symbol for a dash pot, big surprise. Okay, so this is like a circuit symbol, like analogous to an electrical circuit symbol for a mechanical circuit. So we'll be seeing this. I don't know if in this course, but probably in the next course. Okay, so I'm going to attach this to the end, right? Now let's look ahead for a minute. What if I can't do it here, but if you can imagine attaching it very close to the axis here, what effect is it going to have on the wave? There's not going to be any torque. Torque's the important thing here. It's going to, when it's really close there. So it's going to be like it's free. And what happens when I send a free wave down here? You'll notice it comes back and the wave is upright. You can see that, right? I think I'm doing this too high amplitude. Yeah. But you can see that an upright pulse comes back upright. What if I attach this here, or I put a massless extension and I attach it way out here? Now there's going to be a lot of torque because of that moment arm. Now it's going to be essentially fixed, right? We did this before, but let's repeat it. An upright incident pulse, what happens? It's inverted. So it's very natural to think, and again, I don't know if this is rigorous, but it's very natural to think here that if I put it here, we're going to get a pulse that comes back upright. If I put it way out here, it's going to be inverted. Somewhere in between, what's going to happen? It's not going to be there. It's going to be 0, okay? And let me do that. It's approximately at this point right here. Let me show you this. Not real good, right? It's never good. And I suspect this is a pretty high, I think we're outside the linear level here. And this pure absorption of the energy here like that our theory tells us here can happen. If the two impedances are the same, when you have two mediums, our theory tells us you should have complete absorption. This is all linear. And it's the same idea here. So I think what we're seeing is nonlinearity causing a breakdown of this. Because I played around with the position here. This is about as good as I can do. Now, there's one more thing I want to tell you here to make a connection with our theory here. Where's the wave medium here? Well, we've replaced it with this dashpot. However, the dashpot, as we will show later in this class, it has an impedance. When the wave impedance here matches the impedance here, you get no reflection. So this is what I remember from I remember this demonstration, I think. And the only reason I was able to see it is all that money they dumped into education, right, because of the Cold War. You know the idea, right? Obviously, our children aren't learning enough because there's this competing country that has nuclear warheads right off our coast, or they're going to be able to put them up in space, right? So that was a huge panic in this country. And one of the things they did was they said our kids aren't learning enough, so they dumped a huge amount of energy, a huge amount of money into education. All my generation is aware of that. You guys, maybe you'll believe it if you see it in a movie. Okay, any quick questions? How are we doing here? Not bad. Okay. Okay, so remember it's 3 p.m. Pacific tomorrow. Okay.